welcome back. So today we're going to review some special cases of differentiation rules. For our first example, we have the derivative of ln of u. Remember that u represents some sort of function or a variable that we're plugging into natural log for this case. The derivative of ln of u is going to be 1 over u times du over dx, which basically means we're taking 1 over u times the derivative of whatever u is, which is the chain rule, and we've seen that and went over it in the previous lectures as well. Now we're going to take a look at the exponential function. The derivative of e to the power of u is going to be e to the u times du dx. So again, it's just going to be itself multiplied by the derivative of whatever u is. Next, we're going to look at a to the u. Now, a is representing some sort of constant. The derivative of that is going to be a to the u times ln of a multiplied by du over dx. So it's going to be basically the same thing times ln of a times the derivative of whatever u is. Okay, so let's do some practice problems for these three that we just covered. Start with the first one for natural log. An example could be if f at x is equal to ln of 1 plus x squared. Okay, you must recognize that in this case u is represented by 1 plus x squared. This means that the derivative of that is going to be 1 over 1 plus x squared multiplied by what's inside the bracket, or our u in this case, which is just the derivative of 1 plus x squared, which is 2x. Okay, let's start with the exponential function. Let's take, for example, f at x is going to equal to e to the x. Simple case. The derivative of that is simply going to be e to the x. That's it. Because the derivative of our u in this case is just 1, right? The derivative of x is just 1. Let's take a more complicated example. What if f at x equaled e to the power of x squared plus 1? Okay, well, based on our rule, then f prime of x is going to equal to the same thing, e to the power of x squared plus 1, multiplied by the derivative of the exponent, which is x squared plus 1, right? That means the derivative of that is just 2x. Alright, let's go down to a to the power of u. Remember that a is a constant, so let's take an example of f at x is equal to 5 to the power of x. That means that the derivative of that is going to be 5 to the x ln of 5 times the derivative of that x, which is just 1. Let's take another complicated example. What if f at x is equal to 5 to the power of x to the power of 3 plus 2x? Then the derivative of that is 5 to the power of x cubed plus 2x times ln to the power of x cubed plus 2x multiplied by what's inside the bracket, which is 3x squared plus 2, or the derivative of, rather. Okay, the same rule. It's a lot of repetition of all these rules. Okay. Now, unfortunately for most of you who are taking the AP class, you will have to know all of these scary looking trigonometric functions. You should have these memorized. The AP exam will ask you to know some of them. They might be nice and lenient and give you some of the formulas, but most likely they will not. Speaking as a previous student who has taken the AP exam. Okay, the derivative of sine negative 1u, or also known as arc sine, is 1 over the square root of 1 minus u squared du dx. Okay, so whatever that u is that we plug into arc sine, we simply plug that into the function 1 over square root of 1 minus u squared, and then multiply it by the derivative of whatever u is. Notice that you can only have a u value between negative 1 to 1. Okay, so for arc cosine, u is going to equal to the same thing as arcsine, just negative. Okay, the exact same function, just a negative version of that. Now for arctan of u, we're going to have 1 over 1 plus u squared. Okay, very similar but a little different. And we're multiplying that by du dx, which is the chain rule. We don't have any restrictions on u here. Okay, what about arc cotangent? The rule for that is going to be negative 1 over 1 plus u squared du dx, which is pretty much just the negative or the negated version of arctan. For arcsecant, we have 1 over the absolute value of u times the square root of u squared minus 1, du over dx. Again, the derivative of whatever u is. Notice we do have a restriction here where u has to exist between negative 1 and 1, but because it's an absolute value that we're dealing with, means it can only be 1, right? That also gives a restriction. For our cosecant, it's the exact same thing, just going to be the negated version of arcsecant, okay? Du dx, again, same restrictions. Absolute value has to be greater than 1. Now, these look like a lot to practice. Please make sure to check out my video about memorizing these. It's a really cool technique of repetition. Okay, I know it's becoming a long video, but let's do some practice problems. For the first one, for example, if f of x is equal to arcsine of x squared, that's going to equal to a derivative of 1 over the square root of 1 minus x squared squared. Okay? Hopefully you guys got that. And now we're going to multiply that by the derivative of whatever was inside, right? The x squared, that's 2x. The next one, let's take an example of f of x is equal to arc cosine of, say, x plus 1. The derivative of that is going to be negative 1 over 1 minus x plus 1 squared. Multiply that by the derivative of what we plugged inside the arc cosine function, which is just going to be 1, right? X plus 1 is just 1. For arctan, let's take an example of f of x is equal to arctan of x to the power of 2 plus 1. Then f prime of x is going to equal to 1 over 1 plus x squared plus 1 squared. I know it sounds like a lot, but it's really just plugging into the formula. Now we're going to multiply that by the derivative of x squared plus 1, which is 2x. Okay, whatever inside the bracket, we multiply by the derivative of what's inside that bracket. So I love brackets, use brackets. Okay, for our cotangent, we have an example. Let's say f of x is equal to cotan negative 1 of x squared. Then the derivative is going to be negative 1 over 1 plus x squared, put that in brackets, and then square it, multiplied by the derivative of that x squared, which is 2x, right? That's inside the bracket. For secant negative 1, let's take a function f of x is equal to arcsecant of x. Then f prime of x is going to be 1 over the absolute value of x times the square root of x squared minus 1 times the derivative of that x, because that's what we plugged in, right? Which is just 1. For the next one, same idea. Let's say f of x is equal to our cosecant of x squared. Then our derivative is going to be f prime of x is equal to negative 1 over the square root of x squared to the power of 2 minus 1 times the absolute value of x squared, multiplied by the derivative of x squared, which is 2x, again, what we plugged inside the function. Okay, this was a lot, but let's not cry yet. It gets better, I promise.